Part A of this question too was generally done very well. We're given the functions p and q, and we're looking at composite functions. Start by defining pqx and qp of x. So for p of qx, we're going to apply the function p to 5 minus 2x, and p is to square it, so it's 5 minus 2x all squared. And to apply q to p of x, we are going to apply q to x squared, that's px, so we get 5 minus 2x squared. Using this information in part A, we're going to set those two equal and manipulate it to show this. Because we're given this show that answer here, we need to be really clear on every step. Write them down as equal, expand out the left-hand side. Take the terms on the right-hand side over to the left-hand side, or I'm going to add to our 2x squared, subtract 5. Compare that to what we're trying to show, and we can see if we just divide everything through by 2, we'll get our answer. And there we have part A. Coming on to part B, we want to explain why there are no real solutions. We've got two different options. I'm going to show you both options for how to do this. Our first option is to use the discriminant. We are looking at b squared minus 4ac, which is the part within the square root. So remember, if b squared minus 4ac is less than 0, there would be no real solutions. If it's equal to 0, there would be one solution or a repeated solution. And if it's greater than 0, we get our two distinct solutions. Do not start here with the answer b squared minus 4ac is less than 0. Do not start by writing that. We're just going to consider b squared minus 4ac and what that is equal to. So we work out b squared minus 4ac is 100 minus 120 is negative 20. And once we've worked it out, we can therefore say that b squared minus 4ac is less than 0, and that implies that there are no real roots. So our second option, finding the minimum point, and we're going to consider the graph of y equals 3x squared minus 10x plus 10. Two ways of finding the minimum point of this quadratic. I could complete the square or I could differentiate. So there's actually a third option here, but we'll go with completing the square. Option 1 is by far and away the best option here, easiest, most concise, less room for error. Option 2, we're going to complete the square on this. It's not ideal, or not the easiest, but here we go. So I've factored out the coefficient of x squared from my first two terms. I've then taken half my coefficient of x and put it inside the bracket, and then I've subtracted what I would get when I multiply out the bracket again. Multiply the 3 back out across those two terms in the square bracket, and then simplify. So I've now written my function in this form, where I can easily see that my minimum value must occur when my squared bracket is 0, so when x is 5/3. When that happens, that whole bracket goes to 0 and y is equal to 5/3. What I therefore have is a positive quadratic with a minimum point of 5/3 and 5/3. And I can see from there, from that sketch, that it doesn't cross the axis. So therefore, no real solutions to y equals 0, which was their question up here.